Standard mathematics is organized as a federation of distinct provinces. Arithmetic handles discrete recurrence and divisibility, geometry deals with relational form and extension, and analysis governs continuous spectral behavior. The Langlands program functions as a builder of profound, unexpected bridges across these isolated provinces. This framework is known as relational unity. It treats the domains themselves as primary and the correspondences between them as secondary phenomena. But even at extreme depths, these distinct domains perfectly mirror one another. If arithmetic and analysis rely on separate ontological foundations, their structural symmetry remains an unexplained coincidence. The sheer precision of these correspondences suggests that a connective bridge is only a partial explanation for the unity we observe. An alternative framework, closure mathematics, approaches this through the lens of generative unity. Generative unity treats mathematical domains as emergent formations arising from a common structural ground. This reinterprets Langlands correspondences as closure equivalences. A single invariant core is preserved across different sets of formal constraints. Arithmetic, geometry, and analysis then appear as stabilized modes of this shared core. In this model, the mathematical islands are differentiated surfaces of a single continuous architecture of closure. Constructing this model requires defining a domain without relying on primitive objects like numbers or points. This vertical stack represents the generative architecture of unity. At the bottom center is the formal definition for any mathematical domain, the closure regime tuple. The variables x and a define the objects and admissibility, the rules for what is permitted to exist within a specific regime. T and I represent transformations and invariants. These dictate how a structure can move while its core identity remains identical. Bounding the entire tuple is the closure functional, C, which serves as the operative principle of stability for the regime. Altering this functional generates different fields of mathematics. For example, a functional based on lawful recurrence produces the regime of arithmetic. The specific closure functional that stabilizes a local environment is the defining characteristic of a mathematical domain. This generative architecture applies directly to a central pillar of the Langlands program, the equivalence of Galois and automorphic representations. In the closure dictionary, we reinterpret the Galois representation as an arithmetic closure encoding. This encoding dictates how invariant content is preserved under discrete arithmetic symmetry. The automorphic form is reinterpreted as a stabilized closure mode. This mode realizes the same invariant content while forcing it to adhere to continuous spectral and symmetry constraints. Precise Galois and automorphic representations are dual syntax encodings of the exact same invariant tuple. If the languages of arithmetic and analysis are totally distinct, how is this equivalence rigorously proven? Representation theory provides the machinery for closure mediation. Representation acts as a transport vehicle. It externalizes abstract structural symmetries into operator-compatible forms, making the structure portable across regimes. Once the structure is moved, it must be identified. This is the role of L functions, acting as spectral closure signatures. These signatures provide a detectable fingerprint of the structure once it arrives in the spectral domain. When an arithmetic regime and a spectral regime output matching L functions, closure equivalence is verified. Functionality is simply the name for this lawful, closure-preserving transport between different regimes. Representation provides the portability, while spectral signatures provide the visible proof of generative unity. The proven intersection between geometric Langlands and gauge-theoretic physics reveals a structural link between mathematical correspondence and physical reality. This extension is defined as projected closure, the realization of mathematical closure under dynamical constraints like locality and evolution. Physical symmetry is evidence that a projected physical structure is preserving its closure-relevant mathematical content. Conservation laws mark the persistence of this closed mathematical structure as it moves through time. Even quantization is the forced appearance of discrete closure when projected into a dynamical realization. These fundamental laws are inevitable dynamical projections of generative mathematical closure. Crossing the threshold into physical realization alters how a structure is perceived. The projection creates a division between manifest and latent content. Manifest content is the portion of the mathematical structure that is explicitly observable in the physical world. Latent content is the structural scaffolding that remains mathematically necessary but unobservable in the physical projection. This architecture provides a single continuous flow from pure formal closure to local dynamical closure. Mathematics and the physical universe are differentiated layers of a single unified architecture of closure.